Hello. All right. We are working towards understanding extended systems, that it can have many, many objects and particles which may be moving inside their systems. We've talked about various ways we can write down Newton's laws of motion, but typically we've been focusing on either individual particles as our systems or rigid systems where they all share the same acceleration within the system. And to continue generalizing that towards the best version of our understanding of Newton's laws of motion, I can introduce this topic called momentum, which will help us out. Newton wrote down that his second law of motion was that the net force on an object changed the object's momentum, which he defined as m times v. So we can define momentum p as the product of the particle's mass and its velocity. It's a vector, notice. So it is something that both has a magnitude and a direction, and combines both the object's resistance to wanting to change its motion, which you could think of as its mass, as well as where it's going, its velocity. And that is what changes when forces are applied. And then when the mass is a constant, it reduces down to F equals ma. This is a more general version of writing down Newton's second law than writing down F equals ma. I felt almost a little misled when I learned that my high school physics teachers were lying to me the entire time. It's not actually F equals ma. It's F equals the change in momentum. And this way of writing this down actually turns out to be more applicable beyond classical mechanics. Quantum mechanics has formulations that write down that the momentum change of an object or a system changes because of forces. So that does suggest that momentum perhaps is something a little bit more fundamental about the particle than, say, thinking about forces and interactions. Furthermore, as we will see and as you know, momentum is one of these quantities that, under the right conditions, can be conserved, meaning that its time derivative is zero. It does not change with time. Energy, angular momentum being kind of the other two popular quantities that obey conservation laws when the right conditions are met. In these quantities, like the idea of conservation, one, also extends beyond classical mechanics to the other branches of physics, and also is so fundamentally important to our understanding of how nature works that there are these quantities that seems like, under the right conditions, the inherent amount of that quantity for a system cannot change, or it can be transferred amongst different systems. Where forces you think of like they only occur at points of interaction and they only occur during the interaction, so they kind of magically appear and then magically disappear when two objects might separate or something. Momentum, angular momentum, energy, these are quantities where you can actually kind of think of it as I possess a certain amount of angular momentum, and through certain processes can give or take on that amount, different amounts of angular momentum or energy or momentum. These are things that are being kind of transferred amongst different systems. And under some conditions, you can't get rid of or gain any more of those quantities. So they're anchors, in a sense, of, under the conditions that these things can be conserved, they serve as kind of nice anchors of sanity in an otherwise chaotic world where things are happening all over the place and forces and interactions and things are getting transferred left and right. But when you can hone in and find things that can't change, that can be very powerful, not only mathematically in terms of problem solving, but in trying to come up with an idea of what this universe actually is and doing. So let's talk a little bit about momentum and how it changes and when it is conserved today. So Newton's second law says that the change in momentum, the derivative of momentum, is equal to the net force acting on the particle. So written a different way, if I break up the derivative, that says that the change in momentum is equal to a force or the net force rather, times a small amount of time. And I haven't done much, but I still want to give this thing a highlight. Because what this is saying, if we translate this back into English, is that it's asking, the left-hand side is saying, how does momentum change? And then the right-hand side says, when you apply a force over time. Say, how does momentum change? When forces applied over time. I guess when forces are applied over time. And that's important to think about. If we want to talk about that there are these quantities like momentum that can be transferred and gained between systems, they do, in a sense, kind of flow between objects and systems. How can you change momentum? What I've highlighted says that momentum is changed when forces are applied over time. And thinking ahead, you might remember, how does kinetic energy change? Kinetic energy changes when forces are applied over distances, which is different, right? So there are different ways in which different quantities can be exchanged amongst different systems. So if I take that highlighted thing and I integrate it, well, then that also says that the bulk change in momentum, which is the final momentum minus the initial momentum, is then equal to, and that again is just the integral of dp, that is then equal to an integral of force over time, from some initial time to some final time. So I could summarize that as, and the momentum of an object changes in bulk when forces are applied over time, and it can potentially be over long periods of time. T naught, Tf. This doesn't have to be an infinitesimal amount of time. This is sometimes called the impulse momentum theory. So this integral is often called the impulse. Again, even if it's over long periods of time, you usually think impulses as something really fast, like a collision. Also true during those, but in this case, it's also, right, just this is just generally defined as the impulse. Forces integrated over time, or forces being applied over time, changes the object's momentum. So it's also giving us a sense about what forces are doing. When a force acts on an object for an extended period of time, that acts to take the momentum vector and potentially shrink it and stretch it out, or maybe even move it around a little bit. Take, for example, a bouncing ball. I'm not going to care so much about gravity right now. I throw the ball down towards the floor. It eventually gets to the floor. It touches the floor for a bit, and then eventually is sailing vertically back upward. So initially, it looks like the momentum is pointing downward. It has some amount of mass, its velocity is going downward. An interaction occurs with the floor, and then later on, perhaps a long time later on, the ball has some momentum that is pointing upward. So I know that if T initial plus delta P is then going to be P final, if I initially am starting with a downward vector and I'm ending with an upward vector, then it looks like, just by vector addition, that there needs to be some sort of delta P vector that points upward in this case, because that's the only way that I can take a vector that's pointing down and I have to add a vector to it such that it's now just pointing the opposite direction, but upward. I'm not even worrying so much about what the magnitudes are in these cases. So in this case of the colliding ball, so it looks like then delta P points upward, but since that's equal to the integral of the vector F over time, that implies that the force on ball from floor is also pointing upward. and it might be quite large. Again, it also depends on how long the ball is in contact with the floor. So this will generally be a helpful way for dealing with multi-particle systems. But let's stick with just this colliding ball as well for right now. Because this also gives you a way of trying to estimate the magnitude of forces during these really fast collisions. Let's take the bouncing ball again. Oh, and I will say, by the way, did I have to ignore gravity in that description I gave above? No, because there would also be all along, while the ball is both going down, hitting the floor, and going up, the gravitational force is also being applied to that ball over time. But since the gravitational force always points downward, it is always acting to make the momentum of the ball, whatever it is, it's trying to always make it point downward. In the case of it hits the floor does more to have the momentum vector eventually, ultimately point upward, at least right after it collides. If there was gravity, of course, gravity would eventually win out, because once the floor loses contact with the ball, there's no more force being applied over time from the floor. Then it's only gravity acting on the ball, and its momentum eventually does stop and then turn around and become negative again. So again, let's take the ball right before the collision and then right after the collision as well. When it hits the floor, if I wanted to plot as a function of time the force on ball from floor, and if I take t equals 0 as when the ball first makes contact with the floor, right? Really, it's a more complicated function. I actually don't know what it would look like. It would depend on kind of properties of the floor and the ball. Is it a rubber ball? Is it a glass ball? Those sorts of things, and how long it's in contact. But eventually there is some point where it first makes contact, and then eventually a point where it loses contact with the floor, and so therefore the force, of course, must vanish. So the force that, say the floor on the ball is acting on the ball with changes as a function of time. It can be a very complex function. You need very sensitive sensors if you want to actually kind of study the shape of some of these things. And since momentum is the integral of force over time, well, if this graph is just force over time, I know exactly what the integral of force over time is. It's just going to be the area under this curve. It's going to then be the change in momentum of this particle. Figure out that area, you know how the momentum better change. But again, if it's a complex function, I might not be able to really readily write down what that function is. So I might want to instead approximate this as having some average value. It's supposed to be a rectangle. As having some average value. Technically a vector, but this is all 1D. Such that what? Such that this area is the same area as the area I shaded in blue. And so a rectangle, though, is very easy to write down what that area is. It's just F average times the bulk delta T of how long it was actually in contact with the floor. And then sticking with blue, since I shaded it blue, that then is equal to the integral, because I want it to be the same area under the curve of whatever that is. Right, so then you might see we can, again, define the average value of the force to be 1 over delta T, the integral of the actual force between 2 points in time, where delta T is T final minus T initial in this case. So if I can So if I knew, for example, how long the ball was in contact with the floor, I could calculate, and I knew the momentum before the collision and after the collision, I could estimate the average force that the wall is exerting. We could take, for example, suppose it hits the floor with velocity, I don't know, what did I use? About 10 meters per second. And then it rebounds in 1/100th of a second. And leaves the floor with, say, a velocity of 8 meters per second. You could then use the, what's called sometimes the momentum impulse theorem, or just the fact that given this, we can actually estimate what is the average force on the ball from the floor in this case. But we have to be careful with our signs. I guess I need a mass for this thing. So let's suppose it's 10 grams. So I guess mass of ball is 0.01 kilograms. Well, in that case, if I wanted to write that down, the initial momentum before it interacts with the floor, 0.01 kilograms times 10 meters per second. But I have to be careful because if I let me define up to be positive, so it seems like the initial momentum is going to be something like -10 times 0.01. So then that looks like it's going to be, what in this case? 0.1. Oops. And momentum does not have its own unit, so it's mass times velocity, so kilograms meters per second. Something like that. With a negative sign. The final momentum then is going to be +8 times 0.01. So in that case, it's going to be positive 0.08 kilograms meters per second in that case. And that is the final momentum, such that the change in the momentum is then going to be final minus initial, so 0.08 minus the initial negative 0.1. So then that looks like it's going to be 0.1 plus 0.08, or 0.18 kilograms meters per second. Let's see, did I do that right? Yes, it's positive, which makes sense because I know then if this is the same thing as the integral of f dt, which I'm going to approximate as f average times big dt, then that looks like the average force is going to be delta p over delta t, or 0.18 divided by 0.01, or 10 to the minus 2. So then it looks like this then becomes 18 kilograms meters per second divided by seconds, which looks like it's a mass times an acceleration unit-wise, so then 18 newtons. Positive 18 newtons. Right, positive. So this average force is pointing up in this case. So by knowing kind of what happens right before an interaction and right after an interaction in terms of its momentum, you can often estimate fairly accurately things like the average force that's acting on the object. Though again, we want to get towards a more general idea where we don't even need to really talk about forces at all. We can just talk about flows of momentum and energy and angular momentum. But this is a basic idea of how this momentum impulse theory can be used for individual interactions. And again, I could then also write down an integral for what gravity is doing as well. Maybe I'll just write that down real quick, right? I've kind of ignored gravity in this case, or at least I haven't considered it. But then, of course, there's also a gravitational force times dt. But in this case, gravity points downward. So it was minus mg. And both m and g are constant, so this is really just negative mg delta t, right? Which you could compute if you wanted to. So 0.01 times, it's called G10 in MKS units, and then delta t also was 0.01. So it looks like it's 10 to the minus 2 times 10 to the 1 times 10 to the minus 2. So it looks like that's 10 to the minus 3 kilograms meters per second. That's how much the momentum changed from gravity during this interaction. And look, it is very small compared to the 18 kilogram meter per second, or sorry, the 0.18 kilogram meters per second that the momentum was changed by the floor. So in this case, gravity did not do very much during that brief period of interaction. Really, it was the floor doing everything. All right, you could compute an average force, but since it's a constant force, right, F average of gravity is, again, just negative mg. So then that looks like it's 10 to the negative 1 newtons. Again, 2 orders of magnitude smaller than the 18 newtons that the floor did. In cases where there's collisions, we'll see in a bit, often sometimes if the collision is very, very fast, sometimes you can approximate that collision as happening without things like gravity acting on the system, right? Since gravity needs time, right, to do stuff. It needs time to slow down this ball compared to the very brief interaction of the floor ricocheting the ball back into the air. Oops. All right, let's now do a little math, or some derivations. I want to drive our first kind of big conservation result for general systems that can have multiple particles where they're doing their own thing. So let's write down a kind of general coordinate system. So I have some coordinate system that has an origin. And then I'm going to have a system of multiple particles, but I'm only going to draw 3. And I want to study what's going on with this particular system that has 3 particles, which they themselves could be doing whatever they want relative to the other 3 particles, but I'm treating them as a system as a whole. So then, for example, each of them has, that might be mass 1, mass 2, mass 3. They each have a unique position vector. They have their own velocity vectors. It could be that they're tied together, right? And it's actually a rigid system. And then maybe they all have their own velocity vector, but they're all the same velocity vector, for example. But let's treat this very, very generally. And so I'm going to do a derivation where I'm going to write down kind of a very general derivation, but then I'm going to leave some room on the margin to see what that looks like when I restrict myself to just having 3 particles, where it's a little bit easier for me to write everything down. So let's first start by, we have this system, and it has 3D masses in it. Could be there's a billion particles and there's a billion masses in it. And we can define things like the total mass of the system as just the sum of all the masses. Let's also now define the total momentum of the system, which I'll write as capital P, as just the sum of all the individual momentums of all the particles in the system. So I'm writing as a sum over I, where in this case I would be 1, 2, 3. So right, for the specific example, P would be the momentum of particle 1 times the momentum of particle 2 times the momentum of particle 3 for this specific example. But in general, just add up all the momentums. Right, this is a sum of over the system. Okay. Now let's take the derivative of the total momentum. How does the total momentum change as a result? Well, that's just d by dt of, and we define the total momentum to be the sum of all the individual momentums. summing over the system. And there might be billions and millions and billions of particles. And even you can show in math courses, even if the sum goes to infinity, generally you can, even when it's infinite, the derivative can come inside. So the derivative of a sum is the sum of the derivatives. So this is also the same thing as the sum of d by dt of the individual momentums of the system, which I might write as the sum of the individual pi dots. So again, in this case, for our specific example, then it's just p1 dot p2 dot plus p3 dot. Now we have to draw from the fact that let's even just go back and look. The derivative of a particle's momentum is just equal to the net force acting on that particle. So then in this case, this sum is the sum now of, and every p dot is actually the net force that's acting on particle I in this case. So in this case, this is F net 1 plus F net 2 plus F net 3. Now we have to go back up to our drawing and think about what kinds of forces could possibly exist. And I want to be as general as possible, so I want to, categorize them into ways that are most meaningful in this kind of general sense. Well, the particles could, of course, be acting on each other in some way, right? You can think maybe these are a bunch of electrons or gravitating bodies. So it's possible that, M3 and M2 and M1 and M3, that M3 is exerting a force on M2 and M1, or that M2 is exerting a force on M1. But of course, then the opposite has to also be true, right? There also has to be forces being exerted in both directions by Newton's third law. M1 and M3 are interacting with each other, so there are two forces that must arise, right? The total number of forces must always be an even number. So it's possible that these particles within the system could be interacting with each other. So internal to the system, there's interactions. But it could be also that maybe there's a big old finger pushing on M3 from outside of the system, right? Your system is only the three particles, but maybe there's something else from outside that's pushing on M3. Or gravity, right? Maybe, these are three particles, there's gravity coming from outside the system pulling down on all of them. Or maybe it's just a fourth particle that flies by and hits one of these. But we're defining our system to be just these three particular particles, so that fourth particle can come in, do something with one of the particles, then fly away. Or maybe it hangs around, it doesn't matter. We are only talking about the momentum of these particular particles. So I'm going to write this F net for individual particles. And again, I'm summing over for each individual particle. I consider the total force acting on that particle. And I'm going to write it instead as the sum of two terms, right? It's going to be the kind of net external forces that are acting on particle I. So again, the finger, a fourth ball, gravity. And then it's going to be all the net of the force and interactions that are happening within the system, M1 on M2, M2 on M3, M3 on M2, that sort of thing. So I'm going to write this as another sum of, and this is not summing over I, but this is going to sum over all the j's that are not equal to I. And what is this sum over? The force, the interaction forces, right, on I from j. So it's a double sum, it's a nested sum. So take a second to make sure you understand what this is. Again, for a given particle, I am summing up over all the forces acting on that particle from outside my system, plus all the interactions that are happening within the system. And this J not equal to I is just saying that you're not allowing the particle to act on itself. M1 cannot interact with M1. Can interact with M2 and M3. So again, in this case, this gets a little bit longer, right? The net force on particle 1 might then be the external forces on particle 1, which I'm only getting right. That itself might also be a sum if there's multiple things acting on a particular particle, but I'm just going to write it as a single term. Plus the force on 1 from 2, plus the force on 1 from 3. And that's the total force acting on particle 1. We've completed one, in a sense, term of that big ol' sum. Right, then there's the net external force on particle 2, plus all the forces acting on particle 2. So there's on 2 from 1, plus on 2 from 3. And then the external force on 3, plus the internal interactions on 3 from 1, plus force on 3 from 2. And that's the sum of all the forces, right? Again, this ultimately was the sum of all the net forces acting on all the particles. So the sum on the left, if I wanted to write it, right, I can think of it as a sum over I of all the external forces acting on all the particles. And then there's this double sum where I'm summing over every particle, and then for every particle, count all the j that are not equal to I. You might think of how you might code this up as a nested for loop or something. So there's external forces and then all these internal interactions. But here's where having that specific example is helpful in this case to see the magic. It's not magic, it's math. But you know, the gloriousness of what's about to happen by Newton's third law. This force on particle 1 from particle 2 and the force on particle 2 from particle 1 are Newton's third law pairs. So one of them is the vector negative of the other. So when I add them up, I'm going to get 0. On 1 from 3, on 3 from 1, that's a Newton third law pair. They add up to 0. On 2 from 3, on 3 from 2, add up to 0. Notice what's happened. All the internal interactions vanish when you add them all up. All of these are, right, each force has its Newton third law pair here too. That sum, which might be billions upon billions of forces, somewhere in that billions and billions of forces for a given force is its Newton third law pair, so they add up to 0. And that happens no matter how many particles there are. So ultimately, this entire thing adds up to 0. And we're left at the end with this just being equal to the sum over all the particles of the external forces acting on the particles. And since we have likely forgotten where we started, let me just recopy. I started by writing down what is the change in the total momentum of the system. And I ultimately wrote down that it's equal to the sum of all the external forces acting on the particles. That is worthy of a box and a highlight. How does the system's total momentum change? It changes only from external forces. There is no doubt internal interactions going on as well. But by Newton's third law, those are all canceling out overall in a way such that the total overall momentum does not change. I can exert forces. If my system is this apple, there are trillions and trillions and trillions of little interactions going on inside this apple with all the individual protons, neutrons, electrons, whatnot, molecular bonds and such. That overall, though, does not change the total momentum of the entire apple. When I flick on the apple, I can change the momentum of the apple. As I act from external to my system, which in this case is the apple, I can change the overall momentum of the apple. But internally, all those interactions are not changing. It's not creating or destroying the overall momentum of the system, though it might be transferred around again. Again, there could be a jiggling electron on this side where through interactions and whatnot ends up slowing down a little bit, and then some electron over here is now moving a little bit faster. So the individual momentums of the individual particles in the system can change. That's fine. But when I add them all up, the overall amount of momentum is not changing because of the internal interactions, only from my external interactions. And so, if you happen to be in a case where the external forces, the net external forces, go to zero, really it's the net external forces go to zero, then that right-hand side of what I've highlighted above is zero. Then that says that the derivative of the momentum is zero. Or d by dt of this thing is zero. What does that imply when the time derivative is zero? That implies that its antiderivative is just a constant vector in this case. Or, of course, this is nothing more than the conservation of momentum. Also worth a highlight. Lots of highlights in this lecture. If you have a system such that the forces acting on objects in that system are all internal, then the overall momentum of that thing cannot change, like the example I was kind of alluding to with the apple. If there is no external force acting on this apple, its momentum cannot change. So we have derived, again, this isn't magic. This isn't something I just dreamt up that's completely separate from thinking about Newton's laws of motion. We have, in a sense, derived that by using this definition of this thing we're calling momentum, I can then, through appropriate definitions and logical mathematical reasoning, come up with situations where this quantity m times v is conserved. The sum of the m times v's of all the particles in the system is conserved. Right? It is just another way of thinking about what is going on with these systems. That there is this thing called momentum that can be given and taken away. For example, you could think of, if my system is the apple, is momentum conserved? Even if it just sits here and is always stationary. Viewing this lecture and realize what I was about to say in that video was going to be completely wrong. So the idea is, what can I say about whether or not the momentum of this apple is conserved, even in this case where I am holding it stationary in my hand? In this case, if I define my system to be the apple, there are external forces acting on the apple. My hand is pushing up on the apple, and then there's gravity that is pulling down on the apple. But in this case, they have adjusted, or at least my hand's, the magnitude of the force on apple from hand has adjusted its magnitude so to balance gravity. So in this case, while there are external forces, there is no net external force. So in the case of this apple, if it has zero momentum, it will continue to have zero momentum because there's no net external force, even though there are actual external forces on the system, but the net is zero. So in this case also, momentum is conserved for just the apple. If one of those forces go away, like if I were to remove my hand, then of course, then there is a net external force on the apple, just gravity pulling it downward. Its momentum then changes to go from zero to having some downward non-zero momentum as a result. So it's all about, right, the net external force of what goes on. Similarly, I cannot say, if my system is the apple, that momentum is conserved if I'm just tossing it up and down in the air. Because in this case, there is a net external force in most of the situations where it's, in the air, it's only gravity. When it's hitting my hand and coming to rest, there is more force from my hand than there is for gravity, which is what's slowing it down, but that is changing the momentum of the apple. That is taking away the momentum from the apple. Now we'll go back to the video where we can find situations where I can allow the apple to move and still say that the momentum of the system is conserved, but I have to extend my system to be larger than just the apple. But then, of course, I could then extend my system and say, let the system not just be the apple, but let it be the apple and me and the earth. In this case, my hand interacting with the apple and then my feet touching on the earth, and Earth's gravitational pull on me and the apple, all those forces are internal to the system, which is now apple plus me plus earth. So if that was in a sense the whole universe, then momentum would be conserved in that case. But it'd be the momentum of apple plus momentum of Aaron plus momentum of earth is conserved. Though again, individually they could change. I could then start juggling this apple, with my system being momentum, with my system being apple plus Aaron plus earth. And momentum would still be conserved. Of course, the apple's momentum itself is changing. Sometimes it's positive, sometimes it's negative. But then my momentum is also changing as a result, and the Earth's momentum is also changing as a result, such that it's overall conserved in those cases, even though there's relative internal motion and interactions going on. So, super, super powerful. So let's write down some consequences. And some thoughts that I have on this. One, as will always be the case with conserved quantities, try to choose systems so that this is true. Choose systems such that momentum is conserved. Right, you are always free to choose whatever system you want. If you can craft it in such a way such that you can apply conservation laws, all the better for you. Because again, I really like the idea of it being kind of an anchor of just, all these possibilities of things that can be going on. But if no matter what happens, things like momentum better be conserved, that can be very helpful. Sometimes you can't do that though. If I want to just study the motion of this apple, right, it might be that it muddies up the picture if I have the system include me and this table and other things in it too. But sometimes you can be clever about it, where, so let me give kind of two related cases, right? If the momentum is conserved, right, so the momentum vector is a constant, then you can just think of Cartesian coordinates. What does that mean about the individual components? That also means the individual components are conserved individually. Or you can talk about the total x momentum can't be changing, the total y momentum can't be changing, total z momentum can't be changing. Even in arbitrary directions. Right, if I'm thinking Cartesian and I know my momentum is conserved, or I can say x, y, and z momentum is conserved, I could also dot my momentum vector with a vector that points, at a 45-degree angle between the x and the y axes. And then the momentum along that particular direction that kind of diagonal direction is also conserved. Right, so it's along individual directions, you can also think about it being conserved. Or similarly, if a component of F net external is 0, then the total momentum is conserved in that direction, but not necessarily others. The example might be, take the idea of gravity. If I throw this thing vertically, or if I throw this thing even at an angle, when it's in the air, gravity is the only thing acting on the thing, on the apple. And if my system is the apple, there's a external force, gravity pointing downward, being applied over time. So clearly the vertical momentum of this apple is not conserved. You can clearly see it's changing direction. Sometimes it's going up, sometimes it's going down. But there is no net external force acting on the apple in the horizontal direction while it's in the air. So even though the vertical momentum is not conserved, the horizontal momentum must be conserved in that case, because there's no forces acting on the apple in that direction. And then the fourth thing I'll say, which kind of relates to what we were doing earlier with the collisions, is if the interaction is quick. So what I mean by that is, a small delta t. You can often approximate the F net external as being more or less 0 and conserving momentum during the interaction. So what do I mean by that? Like the example of the bouncing ball. If I have my system be the floor and the ball as it bounces off the floor, which then would allow the floor to move as well. If that's a very quick collision, or let's take something that's a little bit easier to visualize, right? I take two balls and I throw them at each other in the air and they hit each other in the air. The amount of time they're interacting with each other is very, very short. So even though in the case of two balls colliding in the air, there is an external force of gravity acting on them, if I treat the interaction as being very, very quick, I can temporarily ignore how the momentum is changing from gravity while they're colliding. Then if I have my system be the two balls in that case, I could use momentum conservation to figure out what they're doing after they stop colliding. And then, of course, I have to bring gravity back. And we kind of saw that with this previous example where, in this case, right, the interaction with the floor, during that very short amount of time had a very large force where gravity didn't really exert much force over that amount of time at all. So the change in momentum from gravity was very small compared to the floor. The floor more or less was doing everything. So we could temporarily ignore, gravity in that case. So this is something to keep in mind for, say, collisions and explosions. The other kind of common example is, you have a firework that goes off. Clearly, after time has passed, the streaming kind of parabolic arcs of all the individual pieces of the firework, right, that's because of gravity. But if I look at right before the firework goes off and right after the firework goes off and make my system all the bits that make up the firework, I could ignore gravity for that small amount of time, and not knowing a single thing about what exact chemical reactions or things is going on inside that firework, I know its overall momentum has to be conserved. It has to overall, whatever momentum it has right before it went off, and then it explodes, and then pieces are going in different directions. But if you add up all the momentums of all those individual pieces, they will still have that same overall momentum vector right before the explosion. So again, really powerful, because I don't need to know anything about what exactly is going off. Is it, blue fireworks or pink fireworks? Doesn't matter. Let me do one quick example of this, and then we can be good. We're about at the 50-minute mark. I'll go fast. I'll go to a different page. All right, so let's take my cat Geo. Here's Geo. Let's make his mass, say 10 pounds, about 4.5 kilograms. He actually is overweight. He needs to actually lose a couple lbs. He's more than 10 pounds. Let's suppose he's 10 pounds and he notices a kind of light cart on wheels. And this cart has a mass of about 2 kilograms, and it's at rest. And it has some pretty smooth wheels, so there's no friction between the floor and the cart. And Geo hops onto the cart and lands on the cart at a 30-degree angle with a velocity of 3 meters per second. So cat jumps on cart, hitting it with V of 3 meters per second at a 30-degree angle from the horizontal. So in that case, let's see, so this kind of ends up being his velocity vector right before he hits the cart, and that's the angle that he hits it with. And the question, what is the resulting motion of cat plus cart? So we have to ask ourselves, now of course we could do this with Newton's laws. When the cat touches the cart, there's an interaction of forces between the cat and the cart. One of those is cart on cat, or on cat from cart. That essentially has to act to slow the cat down so that it's stationary relative to the cart. And then there's also on cart from cat, which then acts to, as you can imagine, the result is they're both going to kind of move to the right. But then I need to know exactly what that force is. What does that force function look like as a function of time as the cat comes in contact with the cart? I don't know. It'd be very hard to write down. It wouldn't be analytical for sure. I could instead, however, use momentum to analyze the situation. So if I have cart and then cat, and I'll draw the cat right before it touches the cart. My system I'm going to identify as cart plus cat. And I'm going to look at I'm going to look right before the cart and the cat come in contact, and right after they're in contact. Which really could be at any point after they come in contact, because we say that the cat comes to rest and just kind of sits on the cart as they coast. So in this case, I get asked what's conserved. The total momentum of the system is not conserved. In this case, they both have vertical gravitational forces acting on them. You might think, oh, if we look right before and right after, maybe we can ignore gravity. Fine. If we were looking at big bulks of time, like when right before it comes in contact with the cart and 2 minutes later, then we couldn't ignore gravity. Well, all that's saying is that there's an external force from gravity, but then the cart is also touching the floor, so there's also force on cart from floor that's external to the system. So in this case, there is a net external force acting on these things. So we probably cannot apply vertical momentum conservation in this case. We can, however, apply horizontal momentum conservation because there is no external interactions going on with the cat or the cart in the horizontal direction, because we're taking the floor to be smooth and frictionless. And there is an interaction kind of between them, but again, that's all happening inside the system. Those horizontal components are all internal. So in this case, the x component of the total momentum is conserved. Vertical is not. There has to be a net external force, particularly when the cat is coming in contact with the cart, because it would want then both of them to then sink into the floor. The floor has to push up and respond as a result. And more or less something has to get rid of the vertical momentum the cat has. It could get transferred to the cart, but then the cart would then move kind of vertical as well, but then it gets robbed from the floor, which is external to the system. So the horizontal momentum is conserved. So then if I can write down the initial momentum of the system, I should make that capital. The initial momentum of the system, which is then just going to be the individual initial momentum of the cat. So if I take right and up to be positive, that looks like this is going to be 3 times cosine of the angle, and then minus 3 sine of the angle, which I already did. So, well, it's sine of 30 degrees. So cosine of 30 degrees is root 3 over 2, and then sine of 30 degrees is 1/2. So whatever numbers those are, kilometers, meters per second. Let's see, root 3 is about, so what, this is like 2.6 maybe, and this is then just 1.5 kilograms meters per second. The final momentum then is going to be, essentially then they're kind of moving as one piece, and they have the same velocity. If we say that the cat kind of comes, stops on the cart. So then this looks like it's going to be something like m cat plus m cart multiplied by the velocity of cat cart, since they both have the same velocity. So this might be something like, what did I say the masses were? 4.5 and 2. So about 6.5 kilograms, and then multiplied by, whatever the cat cart in the x direction is, and then cat cart in the y direction is going to be. But we can only really apply conservation in the horizontal direction. So I can't say anything about the vertical direction, other than I know the constraint is going to make the vertical velocity 0. So in a sense, I do know the answer, but not because of conservation, just because of geometric constraints. So then this implies that I can say what? That about 3 times the square root of 3 over 2 better be equal to 6.5 times the cat cart velocity in the x direction. Which is about what? I got 1.8 meters. Or this implies that the velocity of the cart cat is about 1.8 meters per second squared. Positive, it's moving to the right at about 1.8 meters per second squared. So again, what did we do? We identified which dimensions the momentum was conserved, wrote down the total momentum of the system prior and after, and we were set the components equal to one another. Really, really useful. We'll do lots of problems, of course, on this and build upon this in the next lecture or two.